Good afternoon, everyone. It's always a little difficult getting started in the after lunch time, so I ask you to take a deep breath. I'm from New York, so I'm going to talk quickly. I promise not to get too deep into cryptography today, but we will go a little wider in a conversation regarding what we are considering to be the next wave of crypto infrastructure, and that term is still under development, but our thesis and why we've developed our company has a lot with the changing nature of IoT and where IoT is going. So, as mentioned, I'm John Sirianni, Chief Executive at Tropic Square. Tropic Square is a startup semiconductor company in Prague, Czech Republic, started in 2020 with a very critical mission to develop a secure element chip from the ground up that is completely open source. And by open source, we mean open source software, open hardware, and using a community-driven verification and validation and testing process. We are a division of the Satoshi Labs group of companies. The Satoshi Lab companies have developed very advanced technology for crypto mining and also for coin storage in the form of hardware wallets. And so the very reason we started the company, because of the aggressive forms of attacks that had been seen over the last 10 years in that industry. And in doing so, we've developed something that is truly unique, and I think you're going to enjoy our approach. The name of the company is Tropic for the acronym Truly Open Integrated Chips. Square is because, well, it's square and we're engineers and we're not very creative. So with that, I'm going to go into what I'd like to present today, which is there's four themes that I want to cover. First is how the IoT infrastructure is transforming into and merging with decentralized ledger, open ledger platforms. Secondly, we're going to dive a little bit into why this means that crypto key handling is more critical in this next generation of decentralized IoT devices. Also, then why open and audible semiconductor solutions, we believe, are best suited for this next generation of infrastructure. And then lastly, how that leverages open community innovation, testing, verification, and validation, and what that might mean to some of the regulations going on. So there's a number of terms. If you accept that traditional IoT that we all were born and raised with, I'm an industrial control guy from the 1980s, and so my first project out of school was working on some new technology called Modbus, right? So I go back a ways. And so what we consider to be today's IoT is a growth of 40 years worth of communication technology, data structures, and the like. What we're seeing happening is that's merging with some of these open ledger systems in various industries. There's a term that's forming called transactional IoT. Some are calling it the Web3 of things. Others are calling it M2M payment systems. Others are beginning to call it decentralized physical infrastructure. I don't know that the community has solved the naming problem, but it involves quite a few things. And what I'm going to do is, for those that aren't up on blockchain technology, I'm going to go over some of the basics so that we're all using the same concept before I go deeper into the presentation. So blockchain, as the term I'm using for all decentralized ledgers, is a decentralized shared data structure. Blocks of transactions are linked or chained together via cryptography, and it is public-private key cryptography that we all know and love. It is based on peer-to-peer networks driven by agreement protocols that are automatic in execution. It can be permissionless or permissioned. So Bitcoin as an application on top of a blockchain is permissionless. You don't need to have anybody's permission to use it and build around that open source technology. AWS Hyperledger is permissioned. That's a open ledger blockchain-based technology for corporate enterprise and others who want to control the permission on how the infrastructure is used and developed for. All records are securely replicated and stored across the decentralized network of computers. So that's all records, every so often, are shared in a decentralized manner against all of the servers participating in the network. It's proven to be fault tolerant, even against the largest scale attacks. And the result is that you end up with a transparent, open, immutable, trusted, and tamper-resistant, secure transaction ledger. That's the architecture. So there are projects that are very successful, that are projects that are developing. To say that this is part of the next wave of IoT is basically drawing some connections together between a number of different points in a lot of projects that are happening in particular verticals. What I'm going to explain here is just to compare and contrast traditional IoT with what we're calling transactional IoT. So in traditional IoT, data security is very centralized. Data security in transactional IoT, by definition, is decentralized on purpose. That is its value. Transaction settlement in IoT that we all know and love is intermediary dependent. There's usually a human involved, an organization involved that decides if the settlement actually occurred. Think about banking and the period of time that that takes. By contrast, the transaction speed in anything that's instant, that's a decentralized ledger, is by definition immediate, because each chain in the ledger has cryptographically secured the history of transactions that have occurred prior. Cost, the vision is that traditional IoT is a manual method of operating, and the vision for transactional IoT, machines negotiating with other machines and solving problems, is by definition low cost and also instant. Scalability from an architectural standpoint and a point of failure, traditional IoT being one-to-many and subject to DDoS attacks and single points of failure, whereas transactional IoT, it's a many-to-many, peer-to-peer, and fault-tolerant data structure. Compliance in government is always lacking in traditional IoT as we wait for regulations to be set up and then a lot of paperwork to be processed to determine if the regulations have been met many years into the future. By definition, transactional IoT dependent on open protocols, open ledger systems governed by protocols that are written to software, by definition, immediately are operating at the definition of their structure. And so that's where you get the term code is law, right, in distributed apps, because it is what it is by definition in the code. So the question then becomes, what does regulation look like with that environment? It's a very interesting question. So what does this evolution look like? And we would say maybe this is happening over the next 10 years. To me, IoT, when I got started in the business, was really, it wasn't the Internet of Things. It was the subnet of things. It was me and my organization and my network that I'm responsible for. It's that domain, right? And so I still think of IoT as broken up into 3 layers. Right? There's the thing at the end, there's the connectivity in between, and then there's the orchestration that sits on the top of it all. So from this perspective of comparing and contrasting existing IoT to transactional IoT, we're moving from, at the orchestration level, we're moving from hierarchical control to autonomous smart contracts, and that's from centralized authorities enforcing trust between parties to protocol-defined, self-executing agreements. At the network level, data structure network level, we're moving from centralized to peer-to-peer decentralized, and that's from centralized administrators holding copies of digital transactions to blockchains keeping instant live records of all prior digital transactions. And lastly, connected things. So traditional IoT, things are connected, but they're not necessarily trusted. What we're talking about with transactional IoT is trusted devices, trusted things, carrying out immutable transactions in the device and across a network. So from centrally connected individual devices to immutable device system trust. All right, so let's get into some examples and then some technology that we developed on how to protect some of these devices from the aggressive attacks that we had been seeing. In order to have this conversation, I need to take apart Web 3 versus Web 3.0. There's a lot of noise that's been generated over the years. So let's start from a very simple definition. Web 1.0 that we all lived through. You have mail, blah, blah, blah. Read-only, static internet, 1990 to 2004. Web 2.0 then gets defined roughly around 2004 as we start to have mobile devices enter the network and we see the network cellular technologies move up. The internet at that point is defined as read, write, interactive. Simple. Advertising is the business model. Platforms centralize power, right? Gmail, AWS, Facebook. But the problem is anytime you centralize data and centralize power, you centralize the target. So from a cybersecurity standpoint, we took a lot of data and we put it into one castle, surrounded it with a moat and said, I dare you to get the data. And they said, sure, I'll take those keys and take 20 million records from the US government and essentially poison it, right? So anytime you centralize data, you invite the criminals to target it, you know. Sorry, Your Honor, I rob banks because that's where they keep the money. Surveillance economy is what emerged. What is a surveillance economy? I do a lot of activity on my phone. The platforms collect all that information. They then sell it back to me, right? So this is the world we've lived in. Around 2014, I was working in Silicon Valley for a security company, and the notion of Web 3.0 emerged. By Web 3.0, we mean intelligent and semantic. Hello, Siri. Hello, Alexa, right? Contextual, semantic, some form of responsive intelligence that we can interact with. The idea also laid the groundworks for machine learning and then all the things that we've been talking about here today, AI and augmented reality, and then intelligence at the edge, or the AI IoT. So we use that as a definition of Web 3.0. Subtext to that, the crypto community came along and said, no, we have a different view of the internet. It's Web 3. So Web 3 is read, write, own. I create data, and I own the data. I flip the model around. I own the data. If you want it, big platform, you have to subscribe to it. So this is what was actually created as the blockchain technologies began to proliferate. Digital ownership became a concept. I could use the Brave browser instead of the Chrome browser. Decentralized became the mantra. Peer-to-peer became exactly what the crypto community and crypto infrastructure started to put in place. With the advance of cryptocurrencies came the notion of distributed finance. And then on top of that, Ethereum and similar smart contracts, and then DAOs, which are distributed autonomous organizations. Deep subject. My view, and I think our general view, is that these are kind of merging into the internet of the future. We're going to focus on, for a couple examples here, we're going to focus on the Web 3 point of view, but keep in mind that these are all somewhat merging. So from a Web 3 point of view, right, we have real estate, non-fungible tokens, and smart contracts. So the people in the middle that were pushing paper around are starting to disappear, as a lot of these systems become, as notarization and official documentation become part of an open ledger, which is always live, always immutable, and always trusted. Okay? Fractional ownership of physical gold and other commodities, supply chain transparency. I think you're all maybe familiar with this, preventing counterfeits in the supply chain. Well, if you attach blockchain technology to the transactions at the device level or at the network level, you can begin to track machinery and understand if counterfeit equipment has been entered into the supply chain. Software updates, bill of materials, we're seeing that move to blockchain technologies as well. Defense network security, medical device. We're going to focus on financial for the moment because this is why we were started, digital wallets. Okay, so here's the example. The pictures to the bottom, this device was invented in 2013 by two gentlemen in Prague who started Satoshi Labs. Their friends asked them for a way to securely store cryptographic keys for their Bitcoin. Thank you. And so they developed this device called a hardware wallet. So what is a hardware wallet? Hardware wallet is actually a transaction endpoint for IoT. It's actually a DeFi edge device. It creates, stores, and manages private keys. It interacts directly with the blockchain. So the hardware wallet creates your private key, which then creates the public key, which is your address on the blockchain. So if you lose your private key, you've actually lost your wallet. So, well, what we found during that time period is the aggressiveness of the online attacks was being superseded by physical attacks on devices such as this. Not only small devices, handheld devices, but also other devices such as rings, tablets, and now phones. So the notion of crypto key management in your own personal device or an enterprise device, think of a server that is actually belongs in the CFO's department as part of the treasury to store cryptographic keys. So these are the trends that are going on in DeFi. What we found was that a secure element was absolutely needed as these devices were being designed. In the interest of time, I'm going to speed through this. The original team that were developing these projects went out to the traditional semiconductor industry looking for secure elements, and they found that the security elements were hackable with no special equipment. They also found that a lot of these devices hadn't been updated in about 10 years. They also found that chips that were supposedly certified meant nothing. They weren't certified against the type of attacks they were now seeing in the marketplace. And also, when they went back to the semiconductor companies and said, hey, we found these bugs, basically they were shut down. Why? Because they signed NDAs. And so you can't tell the world about the problems in the chip because, oh, by the way you're using the chip for a crypto device is really out of scope. So the engineers that ran across this problem said, look, security by obscurity doesn't work. We need a transparent system for the semiconductor industry, so they started their own company. In summary, with the attack methods, the ones that were most prominent, and even today are still most prominent in this industry, are laser fault injection, EM probe listening. So basically, while you're stimulating the chip, you're measuring the EM response, and essentially you're backing out where the keys are being produced and how they're being produced, and you can grab the keys. Voltage glitching. Any of these are very common today. So the state of the industry was not great. Black box IP-oriented chips were not fitting the bill. So we started a new company. So now the question is, how do you develop an open security element? Security element is supposed to be secure. So the natural tendency is to assume that you need to have closed IP, secret IP, and keep it locked down. Well, that's actually wrong. We stand on the shoulders of giants. So when you take a look at what Augusta Kirchhoff said, and then Claude Shannon, security of a crypto system must lie in the choice of its keys only. Everything else, including the algorithms, should be considered public knowledge. And then Claude Shannon turned that around and said, one ought to design systems under the assumption that the enemy will immediately gain full familiarity with them. So transparency is really the only path to security. You need to assume that the device that you design is given to the enemy as soon as it's designed. And the only thing that keeps it secure are the keys. That's why I'm happy to announce that we will become generally available. This chip will be available in January of 2025. It is the world's first security element that's completely and totally open. Come upstairs and take a look at the chip and have a conversation with us. You're going to, those of you that care about the details will notice that we have a physically unclonable function. We have multiple TRNGs. The trick here to getting this kind of defense is to take the notion that you all love from enterprise security, which is zero trust, and bring it down into the circuits and the gateware. So the circuits in this device are all cryptographically hardened, and all of the data paths and the customer end data are all protected by very advanced cryptography. So we've launched it. It's available first to the crypto community. Those are the ones that are lined up for our first production. But then we're seeing interest from medical device manufacturers and others that are now looking at putting blockchain, IoT together and securing the endpoint with the latest possible physical security. So I know we're out of time, so I'm going to go into the last slide I have here. Regarding CRA, from our point of view, the CRA defines critical infrastructure devices as critical products such as smart cards, TPMs, and then important products, firewalls, and tamper-resistant MCUs. We believe that the CRA will drive more of a transparent and open design process, and in that, more adoption of security element incorporation into the devices. And as that happens, more and more public testing and publicly available results. And this is consistent with essentially all of the governing bodies' regulations that are on the market today. Open, if you read all of these regulations, openness of what you're doing, the context of what you're designing for, how you've tested it, documented it, and validated it, is subtext to the theme that comes out in all of these. So last one, key takeaways. Secure decentralized ledgers, infrastructures, and traditional IoT are beginning to merge. Attacks are becoming more advanced and less costly to carry out. A device that used to cost $100,000 a few years ago costs $1,000 to attack a chip. So the prices come down, skill levels are going up. This drives the need for better key management in all IoT devices, not just cryptographically secure ones. This drives the need for faster innovation in silicon-based security. Security through adaptability is essential now. We've all talked about CRA and what this means for keeping products alive into the future. Everything that we are building is going to be out on the GitHub. It's all open source. All of the testing and validation will be available. And so this invites the community to test, to validate, and to contribute to the IP that's available for everybody to use. And that gives everyone a faster time to market and a faster time to remediate problems that are discovered. And then lastly, security through transparency, open IP, not closed IP. That's what we're about. Come upstairs and take a look, and be happy to have a conversation with you. Thank you.